Hello and welcome to this second video on variables, and this one we're going to cover a few little bits and pieces loosely continuing on the topic of variables. To start with though, we're going to talk a little bit about comments. So comments in C are just sections of text which the compiler ignores. Now this may not sound very useful. Why would I want to write a section of text that the compiler doesn't pay attention to? But actually these can be really useful. You can leave little notes for yourself or your team in the future to either explain a particularly tricky piece of code or write something that still needs to be done for a particular piece of code or an assumption that you've made over a certain block of code. And so practically these are actually really useful. Now in C we can leave single and multi-line comments, and these are defined in section 6.4.9 of the C99 standard. And essentially multi-line comments you write first of all by doing a / and then an asterisk. To start the comment you then write whatever you want, and then you can end the comment by typing an asterisk and then a /. So this is the end comment delimiter and this is the start comment delimiter. And this is a multi-line comment, so this comment can actually consist of multiple lines which the compiler will just ignore. So I can put a new line in here and say, hey, this is another line, and I can just type whatever I want within the / to * section. And the compiler simply ignores this. Similarly, we can also create a single line comment. So if we go back to where we were, and let's create a single line comment down here just before this line, and we do this in C just by writing 2 /, and then everything else following this on the same line becomes a comment. So we can have C code we actually want the compiler to act upon before the double slashes, just like here, but anything after this is treated as a comment. So here we might actually want to use a single line comment just to comment this line below and say something like, note that some people spell this meters, because people spell meters differently, who knew? And we can leave that in there as a helpful note when we're reading through the code. And while we're sidetracked here, let's just get sidetracked a little bit more. So if we open up Xcode and paste in the code we've written so far, I'm actually just going to show you the disassembly of this code. So you may recall we've talked about assembly code previously. It's a textual representation of the actual instructions that your CPU, your processor, executes. And this is going to be machine dependent, unlike the C code, which can get compiled to various instruction sets for particular processors. So the output I'm going to show you here is going to be both compiler and machine dependent. But if I go ahead and just set a breakpoint here, don't worry too much about what that is, and I just hit play, and we can actually see I've put the disassembly here on the right hand side. So these are the textual representations of the instructions that my machine is actually executing to accomplish the goals of our program. And again, don't worry too much about the specifics of these, particularly as they're machine dependent, but my processor belongs to the x86 family of processors, so you can see we have some variants of the mov instruction here which move values around. We have a call instruction here which is calling our printf function. You can see we also have another call instruction down here which is calling the scanf function. We have this crazy little instruction here which is converting our signed integer value yards into a double value, because we take input from the user as an integer and then we have to convert that to a double to do the calculation for the number of yards. You can see we've got a variant of the mul instruction here to do the multiplication by 0.9144 and so on. So this is just to remind you that C is really just an abstraction over assembly code. And this stuff really does matter, because at the end of the day the assembly code dictates how fast this stuff's going to run on my machine. So we can actually also observe here that most of the operations are taking place on registers. So again, if you recall, we've discussed registers in the past. They're just very fast pieces of memory actually inside the processor. So the processor typically performs operations on registers. And we can see that to be true for the majority of our program. So we're doing our multiplication here in registers. XMM0 and XMM1 are just registers within my processor. And again, remember that this is processor specific. But actually also I can observe from this that some operations aren't taking place in registers. So our scanf, for example, because we had to do that thing, we passed the address of our yards variable to scanf, that requires us to do some things with memory. So that's had to happen in memory and not within the registers. And again, if you're familiar with this particular assembly language, then you could observe that as I am from this disassembly here. But anyway, let's get back on track. So if we stop this and we go back to where we were, okay. So now we're going to talk a little bit about signedness. So some types in C can be either signed or unsigned. So you might have an integer that can hold negative values, a signed integer, an integer with a sign, or an unsigned integer, one without a sign, so one that cannot hold negative values. And we can express these in C using the signed and unsigned modifiers. So variables or types which can be signed or unsigned in C are signed by default, and so choosing to make a variable unsigned is really a trade-off. If you're changing a variable from signed to unsigned, because you're going to use the same number of bits to represent that number, if you make a variable unsigned, you can express a higher magnitude of numbers, so you can represent bigger numbers, but you can't represent those negative numbers. Similarly, if you're switching from an unsigned variable to a signed variable, then, well, the magnitude of numbers you can express goes down. You can express less large numbers to accommodate those negative numbers, which you have to express in the same number of bits. Now, if you're wondering how negative numbers actually get expressed at all in binary, Well, there are a number of solutions, but in modern machines we usually use something called 2's complement, which you can look up if you're interested. But as I mentioned, our variable yards here, which is an integer variable, is actually signed by default, and so our program should deal with negative yards values just out of the box. So let's try that. If we try and run our program, and we put in a negative number of yards, then hey, it actually just kind of works sort of as you'd expect. And if we'd like that to not be the case, we can write the unsigned keyword here, we can save, we can recompile, we can rerun, and now that's going to just put in some crazy value. So we actually get some kind of weird results here because we're trying to put a negative value into an unsigned variable. But let's take that unsigned out for now and keep things as they were. Now we were talking just a second ago about trade-offs in magnitude and the number of values you can represent with a certain number of bits. So this probably raises a question to you, which is, well, how many bits do I have to play with? How many bits does our yards variable have? How large a number can we represent using this int variable yards? And unfortunately, the answer is it depends. So type sizes in C are mostly implementation defined, which means particular compilers can choose what sizes they want to make the basic types to make things fast for a particular platform or architecture. The C standard does provide some constraints, however. For example, signed integer variables must be able to represent values between -32,767 and 32,767, and unsigned integer variables must be able to represent values between 0 and 65,535. And if you're wondering why those numbers are kind of weird, well, they sort of guarantee that you have 16 bits to play with at least. Now those numbers came straight from the C99 standard, and if you're looking for more information about type sizes and the constraints that the standard applies to these, you can take a look at C99 section 5.2.4 for the specifics. One very important constraint that we will discuss though is that char types must be at least 8 bits long, and define the size we call a byte within the C standard. And we can actually talk about bytes of data specifically, so the byte size really is very important. And typically on modern architectures we talk about 8-bit bytes, bytes which are 8 binary digits in size. And actually if we take a look at our program here, we do have some sizing issues. So we define an integer variable called yards, and then we accept some input via scanf into that variable. But what happens if the user specifies some huge value which we can't fit within whatever the number of bits happens to be that our yards variable can hold, which as we've discussed is at least 16 bits? Well, let's try it out. If we actually open up our terminal here and we run the program, and we just put in a bunch of 9s and hit enter, well, we get some kind of weird results which you might not expect. And if we actually look at C99 section 6.5, it turns out that actually overflowing variables like this, so if we just put in a value too large and it ticks over the maximum value which it's allowed to have, is undefined within the C language, which means that literally anything can happen at that point. Realistically though, what usually happens is the values wrap around. So if you have 8 bits and you're playing with 1, 1, 1, 1, 1, 1, 1, 1, and you add 1, then usually what happens is you'll get 0, 0, 0, 0, 0, 0, 0, 0. So you sort of start again. But remember, this isn't guaranteed to happen, at least under the C99 standard. And actually I can show you here that my implementation does wrap around as it happens. So if we open this again, if I actually put in this very specific number, then we'll see we actually get 0 as the number that gets loaded into yards. And if you really want to know why this is, well, you're going to have to look into the 2's complement binary representation and see why we overflow at this exact point. So our program does have some issues here. Someone might run our program, input 5 billion, and just expect our program to work for that value, which isn't necessarily an unreasonable expectation. But we're actually not going to deal with fixing this right now. I'm just letting you know that this is a problem that we have. Now, to sort of help with this a little bit, if we go back to our code, in C99 section 6.5.3.4, the Sizeof operator is defined. Now, I say it's an operator because technically it is an operator, but you can really think of it as a function, but a function that happens at compile time. So this function doesn't execute when you run the program, it executes when your program is being compiled. And what this does is it gives you the size in bytes of the operand of the thing you pass to the Sizeof operator. And remember, the size of a byte is defined by the size of a char, something we've talked about previously and the C99 spec goes into much more detail about. So if we just want to add an extra line here, an extra printf just for kicks, and we print out a number with a new line, and we print out, say, size of a char, well, of course this is going to be 1, because the size of a char is always going to be the size of a byte, so size of is going to say, well, char is 1 byte long. And if we go ahead and compile this, and oops, we get a warning here, so actually I've put in the wrong format specifier. Sizeof actually returns something of type unsigned long, and now we have talked about signed and unsigned, that should make some sense, because long is just another integer type. So let's just go ahead and change that. Instead of D, this should be LU. And let's recompile. Let's rerun. And okay, we see 1 outputted alongside our result. Excellent. And we can actually check the specifics of the size of an integer on my machine too. So if we say size of, well, we could say size of int here, or we can actually just say size of yards, and that will work too. And again, we recompile and we rerun, and sure. And okay, it looks like on my machine, an integer is 4 bytes long. And if we assume a byte is 8 bits long, this means our yards integer variable has 32 bits to play with on my particular machine and compiler setup. Okay, and the last thing I'm going to talk about in this video, I'm sorry it is a bit of a bitty video, but there are just a few different things I wanted to cover, is casting. Now, casting in C is essentially converting one type to another type. And this is actually very useful and something we're going to be using in future. So the cast operator is defined in section 6.5.4 of C99, and essentially has the syntax that if you want to convert, say, the variable yards to some other type, then before the variable you type in brackets the type you want to convert it to. So say we want to convert our integer yards into a char type, then we just type char before our variable, and then of course we have to end the line with a semicolon as usual. And actually let's roll with that, let's printf, let's use %d, and okay. So we're outputting with printf the integer variable yards casted to the char type, and let's see what happens. So if we compile and we run, and enter a value, let's actually say 1000, we'll see, we actually get -24 as the value outputted. And again, this is actually dependent on the whole 2's complement thing. Actually, for simplicity, let's cast here our integer variable yards to the unsigned char type. So this expression here is now of type unsigned char. So again, we save, let's compile, let's run, and this time let's put in something like 256. And we get 0 outputted. And again, if you think about it, this makes some sense. If we're saying that on my machine char is 8 bits in length, then this means it can hold 0 up to 255. So if we put 256 in, we overflow, and thus we wrap around from 1111111 to 000000000 as our unsigned char, and hence we get 0 as our outputted value. Essentially what we've done in this case is we've taken the integer variable yards, which on my machine happens to be 32 bits in length, and we've thrown away those 24 upper bits to be left with the 8 bits at the bottom. So that's really all I had to say in this video. Let's just delete that. I'm sorry it's been a bit of a bitty video, but there are just a few very important concepts that I felt I had to cover. We've talked a lot about types and the sizes of types and what the C standard does and doesn't guarantee in this regard. We've talked about signedness and the trade-off in magnitude. We've talked about the Sizeof operator and casting. And these are all really important concepts going forward. So that is the end of this video, and I will see you next time.